No, didn't want to do that. All right, I think I'm set now. I'm hoping my pen works. But it looks like it's jamming up here already. So, all right, there we go. So, collision theory. It's going to tell why our reactions occur at different rates. They have to collide all the time, but not every collision results in a reaction. Okay, if it's not forceful enough, it's not. If it doesn't have enough energy, it's not going to work. And that energy that it has to hit with is called your activation energy. Okay, so they have to collide. They have to have sufficient energy called your activation energy. And that is the energy that's going to be needed to break those bonds. Okay. And then we've also talked about having the right orientation, where it's the right, the keys fitting right into the lock, essentially. Okay. So if they don't hit at the right spot or with the right speed, or they don't hit at all, you're not going to have a reaction. Okay. And that's why reactions typically occur faster at higher temperatures, because the stuff's going to be moving and colliding much more rapidly. Okay. And they'll also have the higher, which gives them a higher activation energy. So those collisions occur all the time, but they don't also always have to occur with enough energy to do changes. Kind of like car accidents. If you have one in a parking lot and you happen to bump into somebody, and a lot of times there's no damage to either vehicle, okay, or there's damage to one vehicle but not enough. So those collisions, if you want to make them count, be high enough. Okay. Again, increasing your surface area by taking a big chunk of something and grinding it down, that can also lead to a higher number of collisions because you've got more surfaces that you can react upon. Okay, so activation energy, we can look at the lovely Maxwell-Boltzmann graph. Okay, we've talked about him several times, and we can see that the temperature is the measure of that average kinetic energy. Some things are moving faster, some things are moving slower. Okay, so if we had like a Maxwell-Boltzmann that looks like this, only this portion would have enough energy to actually have a reaction occur. Okay. If you wanted to have a reaction occur, you could interject more molecules, and then you would have a greater percentage of them, or not a greater percentage, but you'd have more of them, okay, at that percentage reacting. Or you could increase the temperature, which would cause that to happen as well, okay? And then in general, like I was saying, increasing the temperature by 10 degrees Celsius will result in essentially doubling the reaction rate. Just as a general rule, it's not like a, hard, fast thing, but in general, that's going to happen. Because they are going to have more energy, they've got more activation energy, so they're able to hit with more force. Like if you're going faster in a car and you hit something, you're probably likely to do a lot more damage than if you're going slowly. All right. So again, just kind of looking at the graph here, if you looked at Maxwell-Boltzmann, that higher energy, you're going to have more material here to be able to have that higher activation energy to increase the temperature. Essentially doubling. And a lot of this is kind of intuitive. Again, orientation, so how things kind of collide and hit, they have to be able to hit in the right spot. So for example, here, if we were to have this reaction, don't you start on me this morning. Which way did it go? Okay, there we go. Okay, it's staying. So if we had that reaction, this is our C2H4 here, okay? And it has to collide with the HCl. And it needs to have that Cl hit in here. If we have, I'm sorry, it has to have the H hit in there. If we have the Cl hit, we're not going to have a reaction. If it doesn't hit here at this bond site, we're not going to have a reaction. And so it's got to have that correct orientation and kind of get it lined up the right way in order for it to occur properly. All right, so given this reaction, which set of conditions will result in the highest reaction rate? And they want you to explain in terms of kinetic theory. What do you think? Well, they're all at the same temperature, right? Why would you say 3?
Closer together.
But we have more moles here.
Yeah, but you have a bigger container. Like if you look at the.
Oh, yeah. I get it now. Libby's being stupid. Please just let me have my moment. Thank you. I can't blame it on the board today even. I've got it working. So, all right, yeah. So that is more concentrated. So it's kind of, they're more like likely to hit because they're closer together. Okay. Thank you for my moment. I appreciate it. Although I prefer to have a mocha moment, but you know.
That's right. Or your scone.
My cinnamon scone, yes. Cinnamon scone. I get to have one tomorrow because I'm going to get my hair cut over there. So. All right. So on the first graph, add a line to represent very low activation energy. This is a vertical line. So where would the activation energy hit if we were to have a low activation energy? Let's just draw one, I don't know, like right here. And we're going to call that, this is the way they abbreviate activation energy. E with a subscript capital A. Okay? So if we had a low activation energy and our activation energy was here, that means all of this stuff, you guys, is going to have enough energy to be able to have a reaction occur. Okay? And then they want a high activation energy. Well, high activation energy would be something like here, where very little of this red, a little bit of the blue, and a little bit more of the green are going to be able to have enough energy. Okay, so that would be a high activation energy. If we increase the temperature here in this one, so this is referring to this graph, most of the stuff is already has enough speed. So even if we increase the temperature, there's going to be so little left there. You know, there's not really that much more to add in. So that's not going to make a big difference. But if we increase the energy here on the second one, that would make a much bigger difference because our activation energy is higher. Okay? Collision theory. Everybody's good with colliding? All right. Reaction energy profiles. All right. these are very common on the test to see at least one or two of these on every year's test. Okay. Sometimes they'll have you draw it in. Sometimes they will have it already drawn and ask you questions about it. But this is something that you're going to see very, very regularly on that test. So when we are doing this, you are looking at the energy, the potential energy, and this reaction. If your reactants start out higher than your products end, this is an exothermic reaction because you're giving off energy in the process of creating these products. So just with this little bit shown here on our graph and nothing more, I can tell you automatically that this is exothermic. Your reactants start out at a higher energy than your products. Okay. So that's the way these look. All those pipettes, the glass pipettes there, can get put away too. They go in the same drawer with the burettes.
Oh.
Did you say endo or exothermic?
This is exothermic, and you can. Those go in the little. There's a pipette drawer like underneath where the coffee pot usually is. It has those in it. So energy has exited those bonds and gone out into the world. Okay? So this is called an exothermic reaction. This has left this system and gone out into the surroundings. So you would feel that this system, like if you touched a beaker with this, it would feel warm to you. It's going to give off heat. Okay? Now, if we add in our activation energy, this is what that's going to look like. So from where the reactants started to the top of that peak, that is your activation energy. That is how much energy is going to be required to get the reaction to run. Yes?
So like, is that like, is the activation energy like a specific number or is it?
Yes. Yep. And they will give you values over here. So, 950 and this might be 1100. And then they would say calculate the activation energy and you just subtract. So it'd be 150. And then they might have this guy down here at like, I don't know, 925, 900, something like that. Okay. And then the energy that was given off during the reaction would be 50. All right. So again, like I was just showing you, the activation energy of the forward reaction is given here. And then the reverse reaction would be just the opposite. Okay. Now, we haven't talked about the word enthalpy yet, have we? Remind me. Every year's gets confused. Okay. So enthalpy here is the heat of the reaction, the energy that's given off in that reaction. And like I was saying, you're going to have your products minus reactants, and that's going to tell you how much is given off. So if it's a negative value, that means it's exothermic. If it's a positive value, it's endothermic. We haven't talked about endothermic yet. The opposite of exothermic is endothermic. Not ecto. Because the heat is entering into the bonds and getting stored there. This is going to drive me nuts all day long. And I can't pull it, and I want to clip it because I'm afraid I will.
Do you have a string hanging?
Yeah, and I keep catching it out of the corner of my eye.
Did you not bring a lighter with you to school? Yeah.
All right, exothermic reaction has products with lower potential energy than the reactants. That energy is released then into the surroundings, and then an endothermic reaction would be just the opposite. They give you graphs for these at all? No. So exo is going to look like this. An endothermic reaction is going to look something like that. Those are the differences between an endothermic and exothermic reaction. Good. More time. Okay. All right. The intermediate point then can also be shown in these graphs. Okay. And K is going to count for all the changes in the reaction rate except for those changes in concentration. Okay. That can also mean that a catalyst can be introduced here. And we'll talk a little bit more about catalysts and how they change this when we get to 511. Okay, remember catalysts are able to speed up reactions. And a lot of times catalysts will end up changing that activation energy and lowering it. That's one of the things that catalysts are going to do for you. Okay, so if we look at this, we can see kind of our collisions that we need. Here's our activation energy. It can be shown on this graph in this way for one of the Maxwell-Boltzmann graphs. Okay, and they might ask you which one, would have a higher concentration of product. Okay, and obviously this guy is going to have a higher concentration of product because there's more of it on that side of the activation line. Okay. And then this would be your intermediate, and then this would have less of your material. So you're primarily focusing on this section of the graph here to determine which one's going to have more products, assuming they were all introduced with the same concentrations and that sort of thing. All right. And then over here with this graph, your activation energy is between the reactants and the top of that hump. I'm sure there's some fancy math term for that, but we'll just call it the top of the hump. King of the hill. And then if you wanted to know how much energy was released in the process, that would be measured here to here. And they would have to give you numbers off to the side, obviously. Okay. All you have to do is subtract. And this would be your delta, what they call delta H, which is your enthalpy. Delta H is your change in enthalpy. Delta means change in.
So the on the reactants to the top of the curve, what is that?
Here to here?
Yeah.
That is your activation energy. That's how much energy has to be input to get everything to collide at the right velocity. She's gone. Need to get her some caffeine. I'll need to bring her Starbucks next time. Yeah. Welcome back. Did you drool? All right. Now, There is a fancy equation called the Arrhenius equation.
No. There's 0 numbers in that equation, and I don't.
So what is that?
Oh no, wait. Here's a constant. Okay, that's something.
No.
No.
That's something. It's cool.
I'm not curious. Is that
I guess technically there's also
I
G.
think I'm curious.
Fire is a constant.
but I don't want.
Yeah, this is your constant. This is a temperature. This is your activation energy. Okay.
The fact that there's 0 numbers in this equation.
This is your rate constant. You guys are comfortable with that. You don't have to use it, but sometimes people like to use it because it makes life easier. Because they're nerds, honey. They're nerds.
Scope of the
No.
So that's where I resign.
Keep it like it's easy, you don't get it.
All right. It's out there. If you're nerdy enough to learn about it, go for it. Otherwise, don't. Just let it go. Channel your inner Elsa and just let it go.
It was never.
What, honey? It says that is a frequency factor. So again, if you're fancy enough that you want to look it up and kind of research that guy on your own, you go for it. Okay? It's called the Arrhenius equation. It is beyond the scope of AP. You do not need to worry about it. But if you're a geek and you like worrying about those things and you like learning about extra stuff, go hit it up, okay? We're going to do something a little easier, though. We're going to draw a diagram of an endothermic reaction, which I've already done. Okay? So we're going to start out here. These are our reactants. We're going to have some sort of activation energy, and our products are going to end up at a higher potential energy than our reactants. Okay? The distance from here to here is called the what? Activation energy.
Sorry, I didn't
Okay.
realize the whole curve.
The energy from here to here is the okay. Will my delta H be positive or negative for this? It'll be positive, yes. Because that energy is coming in from these surroundings and getting stored in those bonds. So it's increasing the energy of those bonds. How much is stored in there? If I were to touch the outside of a container while this reaction was occurring, would it feel cold or hot? Cold, right. Because it's pulling energy in from the surroundings and it's going to end up feeling colder to you. Is photosynthesis an endothermic or exothermic reaction? Yeah, you're taking energy from the sun and you're storing it in the bonds of the glucose. Okay? Which means cellular respiration is exothermic. Right, you're getting energy out of those bonds. It is a multi-step reaction. If you get into AP Bio, they will go through all of those different reactions. There's different cycles. There's Kelvin cycle and Krebs cycle, and I can never remember which one's which, but it's there. Okay. So our reactants on here are starting out at 20. And this is how I do these graphs. When I'm doing the graphs, I find where these things are, and I put dots there first before I start drawing stuff. Okay? So my reactions are starting out there. My transition state is at 80, so that's going to be up here somewhere. Okay? And then my products are going to be at 50. it is here. Okay? Just with my 3 dots, endothermic or exothermic? Endothermic. Good. Okay? So I'm going to start out here. I'm going to go up to my activation energy and then down here. The value from here to here is my EA. Okay. So how much was my activation energy then? We can actually calculate that here.
I just have a different question.
Yeah.
Would it matter if it was like drawn more to the right?
What is it?
Yep.
So does the activation energy like line continue on through like infinity and negative infinity?
No.
Or it's
No,
just
I'm
line
just-
points?
Is that a bad, am I doing that bad for math? Does math not like my arrows?
Yeah.
Okay, my math doesn't like, okay, math would not like my arrows. Okay, I will draw it differently then, I'm sorry. It's been a long time, y'all. If I do from here, if I do a straight line there to here, is that better?
Yeah.
Okay, all right. And then that quantity there would end up being 60, and I need my units now. So where am I going to get my units from? Yep, I get it right here. Kilojoules per mole. Okay, and then my delta H. Oh no, don't you do this pointy arrows. Presley's going to call you on that. Okay, that's better now. So that was 50 and 20, so that'd be 30, and that's going to be kilojoules per mole, and that's going to equal my delta H.
I just said I hope Derek gets a 0.0 hours.
Oh, yeah. Yeah, Lippy will be right there with you, honey. Yeah, it's been a while since I've been in a math class, you guys. I think it was 1989 was my last math class. So, yeah. Well, when you're my age, you might be able to. All right, you guys good? Making sense? So you got a little bit of time to work on labs. You got a little bit of time to work on your homework tonight.